Hi everybody, this is our supplemental video lecture on Alkene Nomenclature. Alkene Nomenclature is pretty similar to Alkane Nomenclature with a few minor differences. The first thing you need to do is you need to identify the longest carbon-containing chain that contains the alkene unit. After that, you want to number your carbon chain so that the carbon-carbon double bond is at the lowest position. After that, it's very similar to Alkane Nomenclature. You first want to identify your substituents. Then you want to alphabetize them and arrange them accordingly. And then lastly, you need to use cis-trans nomenclature to identify whether or not your alkene has one stereochemistry or the other. There's also another naming system called E or Z that we will discuss later. Lastly, you need to change your suffix to an ENE suffix instead of an ANE suffix. So the general system for naming alkenes is you first start with your stereochemistry, either cis or trans or E or Z. Then you put a dash in. After that, you put your substituents, another dash, the number at which your carbon-carbon double bond starts, another dash, your parent suffix, and then the ENE suffix. Alternatively, you can also have your stereochemistry, substituents, the parent, then a dash, and then the number at which your carbon-carbon double bond starts, and then your ENE suffix. Either one is acceptable. So let's do a few practice problems. We'll start with this one at the top. We need to number our longest carbon chain, and we want to number it in a way that the carbon-carbon double bond is at the lowest number. So we can go 1, 2, 3, 4, and 5. After that, we want to determine whether it's cis or trans. For this one, you can tell we've got a hydrogen coming off of carbon 2 and off of carbon 3. They're on opposite sides, so this would be a trans. If we were to name this, we would first put our stereochemistry. This would be trans. We don't have any substituents, so we can go straight to our parent. And in this case, we can refer to this as a 2-pentene, or we can call this trans pent 2-ene. Either one would be acceptable for this naming. If we look at our next one, again we want to number our chain so that we're putting that double bond position in the lowest number. So it looks like we've got a heptene unit. And now we want to identify whether or not we've got cis or trans again. Again, we've got two hydrogens coming off of opposite sides. That means that it's trans. And now what we need to do is identify our substituents. Looks like we have a methyl group here, here, and here. So if we piece this together, this would be trans 2,5,5 trimethyl 3-heptene. Alternatively, we could call this trans 2,5,5 trimethyl hept 3-ene. Either one is acceptable. All right, let's take a look at the next two. The next one that we have is a ring system. In this case, we want to number it so that the double bond is at the lowest position. And in this case, we want it to go clockwise to the right. All right, so if we go ahead, we do need to consider whether or not these are cis or trans for some situations. However, with cyclohexene rings, we really will never run into a trans isomer because it is too unstable. So let's take a look at this. It looks like we've got a 1,4,4 trimethyl cyclohex 1-ene. So the double bond starting at carbon 1 and going into carbon 2. Like I said, you normally don't see cis or trans isomers unless you run into rings that are larger than 8-membered rings. So you will occasionally see trans cyclooctene or larger ring systems, but you really don't see it in 7-membered, 6-membered, or 5-membered rings. It's just too unstable. All right, now let's do our next one. In our next one, we need to identify our longest parent chain. So in this case, the longest parent chain needs to contain our carbon-carbon double bond, so we have to start up here. Be 1, 2, 3, 4, 5, 6, 7, 8. Now the question is this cis or trans or neither? In this case, we can't really assign cis or trans because we don't have identical substituents on the same side or on opposite sides. So we'll need to come up with a new naming system to help account for that. But let's continue naming the parent, and then we'll come back to that naming convention later. So the first thing we can see is we've got a 3-fluoro, a 4-isopropyl, and then we've got a 3-octene. The question is, what stereochemistry are we going to include to account for the fluorine being on the same side as that butyl group? We need to come up with something better than cis or trans. And that's where a new naming system comes into play. The new naming system we use is to identify our alkene as E or Z. Cis or trans is just relative stereochemistry. E and Z is absolute stereochemistry, similar to R and S in stereocenters. First thing you need to do is assign the first and second priority for each of the substituents coming off of each carbon. So let's break this down. First thing we'll do is look at this top carbon. I'll label this as red. Over here we've got a fluorine, and over here we've got a carbon. Fluorine's a higher atomic mass, so we will label this fluorine priority 1. So I'll go priority 1, priority 2. Next thing we'll do is look at the other alkene carbon. And then down here we've got a carbon, and we've got a carbon. So it's tied right now. That means we need to look at the next attached substituents. So if we look at this carbon over here, it's attached to 2 carbons and a hydrogen, whereas this carbon is attached to a carbon and 2 hydrogens. That means the isopropyl group on the left will receive higher priority simply because this carbon beats out this hydrogen. So let's go ahead and assign those priorities. Alright, so this would be priority 1, and this would be priority 2. Next thing I do is I draw an imaginary line down my double bond, and then I ask myself whether or not the highest priorities are on the same side or the opposite side. In this case, if we look at these over here and here, they're on opposite sides. That means that when we go to identify these, we need to choose the appropriate designation. If the priorities are on the opposite sides, we would label it as an E, and if they're on the same sides, we would label them as a Z. These come from the German words for together and opposite. Z stands for zusammen, and E stands for entgegen. The way I always remember it is Z. The trick people use is they say the same side in a German accent. I know mine's not very German, but it works pretty well. So Z is always the same side, and E is on opposite sides. So if we were to go ahead and name these, this would be opposite sides. So we would start this with an E, and then put this in parentheses. And then we'd say 3-fluoro, 4-isopropyl, 3-octene. So make sure that you include E or Z, especially if that alkene doesn't have identical groups that you can compare in a cis-trans manner. Z or E can also be used in lieu of cis-trans. You don't have to include both. Z and E is actually the more accurate way of designating stereochemistry for an alkene. All right, let's take a look at this challenge problem. In this challenge problem, we've got more than one alkene in our molecule. Just as with a normal alkene, we want a number so that the alkene starts at the lowest position. So in this case, it would be left to right. So it looks like we've got a nonene derivative. Now what we need to do is identify whether or not each of these alkenes is E or Z. So if we look at this first one, we can't really designate it as one or the other, because in this case we've got 2 chlorines that are identical. We can't compare them to one another. So in this case we can omit that. And then if we look over here, we can take a look at this and we can say, well, this priority, carbon 3, is going to be much, much higher than this hydrogen coming off over here. This hydrogen would be priority 2. And then if we look at this group over here, this would be priority 1, and then priority 2. So the parent chain is going to be higher priority than that methyl group. If we can see, the 1 priorities are on opposite sides, so this would be best described as an E alkene. So I'm going to erase this. If we go to the next one, at carbon 6, we could quite clearly say that, hey, this is going to be priority 1 coming off of carbon 6. The methyl group will be priority 2. And then for carbon 7, priority 1's obviously going to be the ethyl group, and then priority 2 is going to be this assumed hydrogen down here. So we can see that, again, we've got an alkene where the highest priorities are on opposite sides. So this would also be an E. So let's go ahead and erase this. And now what we need to do is to assign each substituent. It looks like we've got 2 chlorines coming off. We've got a methyl group off carbon 5 and a methyl group off of carbon 6. So we've got a lot of information here. And I gave you guys a hint too. If there's more than one alkene in a molecule, you need to put a di, tri, or tetra in front of the ene suffix. So let's take a look at this, and we'll start off with naming it. In this case, the alkene coming off of carbon 1 has no stereochemistry. We can skip that. However, the alkene starting at carbon 4 is an E, so we'll label this as 4E, comma. The alkene starting at carbon 6 is also an E, so we'll do 6E. And then we'll put brackets around this, and then a dash. And in this case, we've got a 1,1 dichloro. And then we've got a 5,6 dimethyl. And in this case, our parent is 9 carbons long, so it would be a nona. And we've got 3 different alkenes. One starts at carbon 1, the second starts at carbon 4, and the third starts at carbon 6. So we call this a 1, 4, 6. And then we would put a triene to indicate, hey, we've got 3 alkenes. One starts at the 1 position, one starts at the 4 position, and one starts at the 6 position. And you can tell their relative stereochemistry by looking back at the beginning over here. All right, I hope that helps, but if you have any questions, you're always welcome to email me.